Okay, let's start. Uh, Today we will study Thevenin's theorem and Norton's theorem. Thevenin's and Norton's theorem are very important for big circuits where only we want to check the only resistance of a load. What is the variation based upon the big different circuit? So what we studied before is superposition theorem and source transformation we studied, right? And linearity of the sources we studied. So now come to the Thevenin's theorem. Thevenin's theorem states that a linear two-terminal circuit can be replaced by an equivalent circuit consisting of voltage source Thevenins in series with a resistor R Thevenins. That is RTH means R Thevenins, VTH means Thevenins. Where Thevenins is the open circuit voltage at the terminals and R Thevenins is the input or equivalent resistance at the terminals when the independent sources are turned off. Here you will get more clear when I will explain with the circuits. Then it will more clear. So what it is exactly telling, it must be a linear circuit. Maybe whatever the big size, we won't care that one. Just we have to replace that circuit by its equivalent circuit with a Thevenin's voltage source and resistance R Thevenins in series to that voltage source. Then we can connect the load resistance, which we want the behavior of that load resistance. Then we can continue. So how it works? Let's see. See here, we have a linear two-terminal circuit is here, and here there is a load. Load means here generally linear and passive elements means resistance only. It may be of any form, motor form or any other form. It must equivalent to the load with a resistance. Now in the linear two-terminal circuit on the left side, it may be have a much bigger circuit. So solving with KCL and KVL, it's very difficult. So that's why what we can do, we have to replace that big circuit, linear two-terminal circuit, with a voltage source called Thevenins and in series with a R Thevenins. Then connect it to the load. Now whatever you change the voltage here, then the load value behavior will come out. Now Thevenins and R Thevenins are in series. As per the source transformation, voltage source and resistance should be in series. And the current, when you come to the Norton's theorem, current source and thus R Thevenins or R Nortons will be in parallel. Current source and the resistance will be in parallel. Okay, so what is the rules? According to Thevenin's theorem, the linear circuit as shown can be replaced by that in the figure. The load in the figure may be a single resistor or another circuit. The load may be a single resistor or another circuit, maybe. But generally it will be a single resistor. And this is the equivalent of the Thevenin's, which is nothing but a output for the linear two-terminal circuit. Now the circuit to the left of the terminal is known as the Thevenin's equivalent. In this circuit, the left side of the A and B terminal is called the Thevenin's equivalent circuit. In the figure, the Thevenin's equivalent voltage Thevenins is the open circuit voltage across the terminals. That is, it is the open circuit voltage across these terminals A and B. Here also A and B. This is the open circuit voltage for this complete left side circuit. Okay, so it's also called Thevenins. Also, it's called open circuit voltage. In the figure, the Thevenin's equivalent resistance. What is the resistance now? Is nothing but is the input resistance at the terminals when the independent sources are turned off. That is R Thevenins is equal to R in. What it means, just we have to remove that load and see from this end. From the right side, we have to see to the left side and check what is the circuit behind this linear two-terminal circuit in between terminal A and B. So left side, we have to see the circuit and check whether any independent sources are there. Independent sources are like voltage source or current source. If voltage source is there, we have to short circuit. If current source is there, we have to open circuit. Now, then we can find the equivalent resistance by elimination technique. That is series, parallel and star delta, whatever technique you can use it, you can use it. So like this, we have to find the R Thevenins, which is nothing but R input. That is at the terminal A and B on the left side. What is the input resistance we have to find? So this is R input. This is your Thevenins. So now let's see. To find the Thevenin's resistance, first we will go for the Thevenin's resistance. How can we find? We need to consider two cases. First case, see the circuit for the Thevenin's resistance. If the network has no dependent sources are four types: voltage control, voltage dependent source, and current control voltage dependent source, current control voltage dependent source, current control current dependent source. These are four types are there. If any are there, what we have to do? Then we have to think later. First, if the network has no dependent sources, then we turn off all the independent sources, any other than the dependent sources, like pure voltage source, which is not depending on any other sources, pure current source, which is also not depending on any other branches or voltage sources. Then we have to turn it off. What is turn it off means? We have to short circuit the voltage source and open circuit the current source. Then Thevenin is the input resistance of the network looking between the terminals A and B. Between looking the terminals A and B, the Thevenin is your resistance. Let's case 2. Then case 2, what we have to do? If we have a dependent source, let's say. Case 2. So if we have dependent source, the problem will come. So what we have to do? If we have dependent source, then we have to apply some voltage to this terminal A and B or current. Then we can find what is the equivalent resistance. If the network has dependent sources, we turn off all independent sources, like in case 1. We apply voltage source V0 at terminal A and B. We apply voltage source V0 at terminal A and B and determine the resulting current I0. Then find the I0, what is coming at terminal A. What is the current I0? Then Thevenin is nothing but V0, what we applied here, divided by current I0, as shown in figure. So that will give the Thevenin easy. When we have a dependent voltage sources, it is very dangerous. Okay, with some complication will come when dependent is there. But simple technique, we have to apply some voltage. That V0 maybe 1 volt, 2 volts, whatever you want, you can apply. Then find I0 to this circuit. Then V0 divided by I0 is nothing but Thevenin. Directly you will get it. Or you can apply current source also. Another case, 1 ampere current you can apply. Then find the V0 here. So once we know the V0 divided by I0 is nothing but same Thevenin. Alternatively, we may insert a current source I0 at the terminal AB, as shown in figure. Current source. Now we are applying current source. Here we apply voltage source. Now we apply here current source and find the voltage V0. And again Thevenin is given by V0 by I0. Now in either approach, in these two cases, maybe voltage source or current source, when you are applying to the dependent sources circuit, in either approach, we may assume any value of I0 and V0. You can assume anything. Here V0 you can assume 1 volt. Here I0 you can assume 1 ampere. Small quantity is enough. So, or even use unspecified value of it. So like this we can find the Thevenin easily if we have dependent sources. Independent, no need to apply any voltage source, current source. Just short circuit the voltage source inside that circuit, open circuit the current source inside the circuit and find the equivalent resistance by series parallel combinations. Now, as mentioned earlier, a linear circuit with a variable load can be replaced by a Thevenin equivalent exclusive of the load. Means without the load, it can be represented with a Thevenin equivalent. It shows like this. The equivalent network behaves the same way externally as original circuit. Now we have removed the complete circuit and we place a equivalent voltage source and a equivalent resistance in series. Now these two components, two branches will behave like a original big circuit. Whatever the circuit we had, it will behave like that only. No changes in that. Now see here. So here once you find the Thevenin and Thevenin, and this is your RL, load resistance. So consider the linear circuit terminated by RL. This is the RL load where we are connecting this linear circuit. For this linear circuit between terminal A and B, we have to find Thevenin's voltage source and resistance in series. That's called Thevenin's resistance. This is called Thevenin and this is called Thevenin. RL is as it is. So this circuit Thevenin and Thevenin will behave as it is like linear circuit. So the current IL through the load and the voltage VL across the load. voltage across the VL and current through the load are easily determined once the Thevenin's equivalent of the circuit at the load terminals is obtained. Means once you find the V Thevenins and once you find R Thevenins, and now we are connecting back the load resistance, then these two resistance will be in series and this is the voltage. So V divided by total resistance is the total current, that is IL, right? So directly we can get it. So that equation is nothing but IL is nothing but total voltage, that is V Thevenins, divided by R Thevenins plus RL, because these two resistors are in series. Current in the loop is single. So like this. Now what is voltage? IL we got it. What is the voltage at RL? Nothing but current voltage division rule. What is the voltage division rule? VL is equal to RL times IL. That is its own resistance divided by total resistance plus into multiplied by V Thevenins. Or you can substitute this IL, that is V Thevenins by R Thevenins plus RL multiplied by RL, which will give VL. So this V Thevenins, the voltage will divide in RL and R Thevenins. These two places it will divide. So what it will, how much divide is nothing but your VL. VL is nothing but its own resistance divided by total resistance multiplied by Thevenin's voltage. So this is your how to find IL and VL for a big and unknown circuit. Means unknown means here complex circuit. Just we are simplifying with only three branches, not more. Previously this linear circuit may be so much big, we don't know. Means it may surely big. That's why the Thevenin's theorem come into picture to solve such cases. Because we want to see the RL behavior when the linear circuit is changing. When linear circuit is changing, its voltage and current may be big, may be complex. When it's changing, we want to see the change in the RL. That is voltage and current. So the linear circuit, every time we cannot solve from step 1 to step infinity. That is apply KVL, apply node analysis, apply mesh analysis. We cannot do every time. So for big circuits, we make a equivalent circuit. That is called a Thevenin's equivalent circuit, V Thevenins, R Thevenins. Then we put this V Thevenins, R Thevenins in series and another RL in series. So whatever changes you want to make in the linear circuit, it will tell this one. Then you will get the RL. So like this, you have to find the V Thevenins. Now one example. We have two examples in Thevenin's circuit. One is with independent source, another one is with dependent source. So both will covered, inshallah. So now first, this is your circuit. What are the items we have here? One voltage source, one current source. Both are independent. One voltage source, one current source. And now 1, 2, 3 resistances in between terminal A and B. And this is the RL, which is called load resistance, which is fixed one. In this RL only we need the current and voltage. Remaining circuit is the linear independent circuit, this one, where we have to find equivalence for this circuit on the left side of the A and B terminal. So, okay, what is the question? Find the Thevenin's equivalent circuit of the circuit shown in figure to the left of the terminals A and B. To the left of the terminals A and B, we want to find the Thevenin's equivalent circuit for these branches. 1, 2, 3 resistances, one voltage source and one current source. Total how many? 5. So 5 elements we are minimizing into 2 elements or 2 branches. One voltage source, one resistance. That's it. So the how we are minimizing, we can see. So then find the current through RL. So we need a current through the resistance RL when RL is resistance having 6 ohms resistance, 16 ohms resistance and 36 ohms resistance. It's varying. So see, first time 6 ohms. Now without the Thevenin's, you have to solve everything. KCL, KVL, loop analysis, mesh analysis. Put it and you have to solve. Oh, in this RL, this is the current. Again change the RL to 16 ohms here. Again solve the complete with same method. Mesh analysis, loop analysis. How many loops? 1, 2, 3 loops. Node analysis. How many nodes? 4 nodes. So every time when resistance is changing, every time we have to do from 0. We have to do from step 0 we have to start. How much time it will take? How much complexity it is there? So that's why only we want to change RL here every time, right? So if we have an equivalent circuit on the left side with a one voltage source and one resistance, then easy to find every time. Just change the RL, you will get the one step answer. Only one step answer, not more. Like that's why we got the Thevenins. Okay, how to solve now? What is the first step? Find the R Thevenins, right? Thevenins resistance. What do I have to do? Remove this RL and see from the A to B inside on the left. From A to B terminal, see on the left side. What to do the step in that step? Off the sources. Independent sources should be off. Off means here what? Voltage source should be short circuit. This 4 ohms will be here becoming a short circuit here, and it will be parallel with the 12 ohms. 12 and 4 will become parallel. Next, current source should be open circuit. Remove it. Now it will be removed. So this 1 ohm will be there and will come in series with these two in parallel. Okay. Okay. Now we find the Thevenin, R Thevenins by turning off 32 volts voltage source, replacing it with a short circuit, what I told, and 2 amp current source, replacing it with an open circuit. The circuit becomes what it shown in figure. So it becomes like this. See, this I short circuited, 4 and 12 will be in parallel. Now I open this one, so 1 ohm will be as it is. Now I have to see between terminal A and B from the right side to the left side. Now solve, when you are seeing from the right side to the left side, how to solve? From left to right. Solve from left to right now. Because I am seeing from this side. I cannot go from right to left now. We have to see from left, we have to see from right side. Then we have to start the solving from left to right. At the end, from the end to the starting point. This is the end point. 4 ohms is the end point. So now 4 ohms and 12 ohms will be in parallel. 4 ohms and 12 ohms will be in the parallel. Plus whatever the result is coming. Plus 1 ohms in series. So what is the 4 ohm and 12 ohm parallel? 4 multiplied by 12 divided by 4 plus 12, 16. So we will get 4 ohms. Here you will get 3 ohms plus 1. This is 4 ohms. So R Thevenins we got in one step. Now we need next step, Thevenin's voltage. Voltage we need. For voltage what we have to do? Because it's a dependent, right? Sorry, these are the independent sources. So no need to consider or add voltage or current source in terminal A and B. We can directly find with the loop analysis. See, the original circuit is this one. This is the original circuit. Keep it here. Just remove the A and B terminal load resistance and start analyzing, finding the voltage. What is the voltage is nothing but at this terminal V, A and B. At this terminal A and B, what is the voltage is nothing but Thevenin's it is. So, first loop, second loop we have. First loop equation, how can we write? Anyone? Already we did so many things. First loop equation. What is the first loop equation? Minus 32, correct? 4I1 plus 12I1 minus I2, right? So first equation will come here. Minus 32 plus 4I1 plus 12I1 minus I2, which is equal to 0. Now rearrange this, you can get I2 equal to minus 2 amperes. Why? Why I2 is, I2 is equal to minus 2 amperes. Why it is coming here? Check here, in the second loop, the current what we are assuming is this orientation, that is clockwise, and the current in this branch is upward, okay, and this I2 is equal to this current, but the direction is opposite. So because the direction is opposite, I2 is minus 2 amperes. Now substitute this I2 in this, you will get the I1. Okay, now I1 you will get 0.5 ampere. So we got the I1 now. Now what is the Thevenins? So Thevenins at the point A and B is nothing but you have two options here. We can have two options. That is this one. In this voltage, this point, what is the voltage is equal to this point voltage. Why? Because this resistance, any current is flowing in this resistance? Anyone? Is there any current flowing in this 1 ohm resistance? It's series, I know. After that, it becoming series. After this parallel, it becomes series. But is there any current will flow? Yeah, good point. For current flowing, it must be a closed circuit, right? So because it's an open circuit here, there is nothing here. We already removed the RL here. RL we removed and we are analyzing the voltage and the current behavior in between A and B. So there is no current here. So whatever the node is going, where the node is going, this A up to here or up to here, these are the same node. And B is node is going, common node is here. So what is the voltage in 12 ohms is nothing but your Thevenins. Okay, what is the voltage? Here is nothing but VThevenin, or two options are there. Voltage in the 4 ohms and 32 ohms also VThevenin, same, parallel is same voltage. All parallel branch have same voltage. Now you can, first option, second option will come. This one, 32 minus 4 into I1. What is I1? 0.5, right? So 4 into 0.5, how much? 2. 32 minus 2, how much? 30 volts. So in this, from these two branches also we find VThevenin, it is 30 volts. 30 volts. Now if you find voltage at the 12 ohm resistance also, same. What is that one? 12 times I1 minus I2. So 12 times I1 minus I2. 12 times 0.5 minus of minus, that is plus 2. That is 2.5. 12 into 2.5. It is 30 volts. So both way it is correct. If you use this branch 12 ohms only, VThevenin is we got. If you want to use this node analysis from this branch to this branch, 32 minus 4 into I1. This also comes same. So this is how we find the VThevenins. Now we have to find the RThevenin, load resistance. We have to apply and find the load current, and we can proceed. Now same example, continue. Now another method I told you, that is 32 minus VThevenins divided by 4 plus 2. In that node analysis, if you type that also will come. So then we will get VThevenins 30 volts by node analysis also. Okay. Now this is your final circuit with VThevenins and RThevenins and load resistance. Now load resistance is varying. How many types of resistance we added here? Three different resistances we added here. 6 ohms, I think, and we have another 2. Okay, when it is having 6 ohms, let us take. Now we can also, okay, that Thevenin equivalent circuit is shown in figure. Then RL is known as. Now current in the RL, in the current in the RL is nothing but, by using voltage division rule, we can write VThevenins divided by total resistance. That is 30 divided by 4 plus RL. That is VThevenins, RThevenins already known. VThevenins, RThevenins already known. Only unknown is RL. So you can write the general equation IL equal to, that is load current, 30 by 4 plus RL. Now every time you have to change RL and get the current in the load. So when RL is 6 ohms, just substitute RL is 6 ohms here, 6 plus 4, 10. Now it is 3 ampere. 30 by 10, 3 amperes. Now when RL is 16, so substitute here 16 plus 4, 20. So 30 divided by 20, 1.5 ampere. Now when RL is 36, RL is 36, 36 plus 4, it is 40. So 30 divided by 40, it is 0.75 amperes. So like this, we have to find the VThevenins, RThevenins, then load current or load voltage, whatever you want, we can do it. Here only he asked for load current, so we can stop here. Sometimes it may ask for the load voltage also. For load voltage, voltage division rule we can apply. That is load resistance divided by total resistance multiplied by VThevenin's voltage. That is a load voltage. Now coming to another example with the dependent sources. Another example with dependent sources. So find the Thevenin's equivalent circuit at terminal A and B. Here only we need the equivalent circuit, not much. No need of load current or load voltage. Now this is the circuit. See, complex circuit is there. How many branches? 1, 2, 3, 4, 5, 6 branches. Now terminals are A and B. In between A and B terminals, we have to find VThevenins. We have to find the RThevenins. Let's start with the RThevenins first. So what we have to do for RThevenins first? Just we have to switch off the source voltages or source currents. What is switch off source voltages? We have to open circuit this current source. Then this is dependent. So dependent source we should not touch. Okay. Now we have to find the equivalent resistance here. Just start. This circuit contains a dependent source, unlike the circuit in the previous example. Okay, to find RThevenins, we set the independent source equal to 0. Independent source equal to 0. How? We have to open circuit that one. But leave the dependent source alone. Because of the presence of the dependent source, 2Vx. However, we excite the network with a voltage source V0. Now we apply a voltage source here, V0, connected to the terminals. As shown in figure, we will see it. Yeah, we have to apply a voltage source V0 connected to these terminals. Then we apply a mesh analysis or loop analysis. Then we can find the different currents and voltages. Okay, we may set voltage V0 is equal to 1 volt. I will put 1 volt only, not much value. Okay, since the circuit is linear, our goal is to find the current I0. Once you find the current I0, V0 is known. So then R Thevenin will be V0 divided by I0. So then obtain R Thevenin, which is nothing but V0 by I0. Now V0 we are assumed 1 volt. So 1 divided by I0. Just we have to find what is I0 to get the R Thevenin. Okay, alternately we may insert 1 ampere current here. Another way method is there. Insert the 1 ampere current here. Now find the what is the VO here. Then same R Thevenin is equal to VO divided by I. So VO is nothing but your R Thevenin. So then VO, then R Thevenin is equal to VO divided by 1 ampere directly. So like this we have to have two options. Either use voltage source of 1 volt you can apply, or current source of 1 ampere we can apply here. Okay, I applied now voltage source. Now check the loop analysis. So we have how many loops now? 3 loops. So I1, what is I1? I can give directly. It is leaving. Leaving means what? I1 is equal to dash. I1 is leaving the plus terminal. Minus. Right? No. Yes, entering in the minus. So that's why it will be I1 is equal to minus Vx. I1 is nothing but minus 2Vx. Okay. What is Vx? It is nothing but 4 times I2. Vx is nothing but 4 times I2. Vx, what is the voltage here? Current is leaving. So plus other. So 4 times I2. Okay. So we will see for first loop. Okay. Applying the mesh analysis to the loop 1. I consider which is the loop 1. Result in minus 2Vx. 2Vx. Yeah, here. This is the first loop. Okay. So this is minus 2Vx. I can take because current leaving plus this one. 2I1 minus I2. 2I1 minus I2. This one. Okay, this much is equal to 0. Or Vx already we know. What is Vx? It is 4I2. Vx is nothing but I1 minus I2. Vx, where is it? Yeah. How is getting? Yeah, rearrange this one. Sorry. Rearrange this one. You get Vx is equal to I1 minus I2. Just you rearrange this one. Take I1 minus Vx other side, cancel 2 and 2. You will get Vx is equal to I1 minus I2. One equation we got. Another equation from here also we will get Vx is equal to 4I2. We can substitute later. No problem. So next, but see, minus 4I2 is nothing but Vx. This minus 4I2 is nothing but Vx. Because source is plus and minus is mentioned here. Current leaving, anything the current leaving from this, any branch is nothing but considered as minus. So it is minus 4I2. That is Vx. If it is current entering this plus terminal, then it is plus 4. So now it is leaving. So minus 4I2. So which is also equal to I1 minus I2. So we can find I1 is equal to minus 3I2 from this equation. Now we got I1 and I2 relation. Now find from the loop 2 and 3. So loop 2 and 3. So loop 2, what is loop 2? 4I2, that is plus 4I2 plus 2I1 minus I2, 2I1 minus I2. Now next 6. 6I2 minus I3. 6I2 minus I3. Now substitute what is I1 in terms of I2. Now another equation for this one. Loop 3. 6I3 minus I1, that is 6I3 minus I1 plus how much this one? 2I3 plus 2I3. Now what is the voltage here? 1 volt, V0 actually, 1 volt. Now entering in the plus terminal, so plus 1 equal to 0. So we have 3 equations now. Which equations? I1 equal to minus 3I1, minus 3I2. Now in this I1 and I2 and I3 is I1, I2 and I3 are unknown. So 3 equation, 3 unknowns. Can we get the result by elimination technique? Sure. I1, I2, I3 can be find because we got 3 equations and 3 unknowns. We can get easily the result. So solving, we can get I3 equal to, because we need I3 only. For getting the R Thevenin, we need I3 majorly. Forget about I1, I2. Directly we need I3. So I3, if you find minus 1 by 6 ampere we are getting from this solution elimination technique. By elimination technique, I3 is getting minus 1 by 6 amperes. Now, but I0, what is I0? minus I3 because it's opposite. I3 is going downwards, I0 is going upwards. Is inserting in the circuit. So minus I3. So I3 is already minus 1 by 6. So it becomes plus 1 by 6. 1 by 6 amperes is your I3. Now what is R Thevenin's? V Thevenin's divided by V0 divided by I0. So what is V0? 1 volt. Already we assumed. So 1 volt divided by I0. I0 we got 1 by 6. So 6 will go up. So it becomes 6 ohms. So like this in 1, 2, 3, 4, 5, 3 to 4 steps we got R Thevenin's because of the dependent voltage source. If it is independent voltage, independent source, directly in 2 or 3 steps we will get directly. No need of considering this voltage source, adding some 1 volt or 1 ampere current inside. So now we go for the R Thevenin's. We got it. Now we need V Thevenin's. So what is V Thevenin's? So for V Thevenin's, same loop. We have to check with considering all the source currents and everything. Source current should be as it is. The dependent sources should be as it is. Everything should be as it is. Then we have to find the V Thevenin's between terminal A and B. So what is the between terminal A and B? VOC is equal to V Thevenin's. And this VOC is nothing but voltage across 6 ohms resistance. Voltage across 6 ohms resistance is nothing but VOC. Because 2 ohms resistance is there, but there is no connection, there is no loop for it, there is no closed circuit for it. So no current will flow in 2 ohms. So the VOC is nothing but the voltage across the 6 ohms resistance, which is nothing but 6 multiplied by I2. 6 multiplied by I2 is nothing but your VOC, which is also equal to VThevenin. So find I2, you will get the solution, VThevenin's. Okay. So for getting I2, we need the further 2 loops, I1, I3 and I2. Now apply the loop mesh analysis for first loop. What will be the first loop? Current is leaving, current source, and this also in same direction. So I1 is equal to 5 ampere as it is. No need of any loop equation here. This is the current source. So I1 is directly 5 amperes. Okay. Now coming to the second loop. What is the second loop? Here or here, anything. So the second loop is nothing but Vx also we can take, but current is leaving. So minus Vx. Current is leaving. So minus Vx, or we can write 4 times I1 minus I2 also you can write. Both way possible. So minus Vx plus 2 times I2 minus I3. 2 times I2 minus I3 plus 6 times I2. Because there is no other current here. 6 times I2, one equation. Coming to this one, what is the loop? Current is leaving. So minus 2Vx plus 2 times I3 minus I2. Then solve the 3 equations, you will get it. So first one, I1 is 5 amperes. In first loop, I1 is 5 ampere as it is. Now second loop, I think he took this one second loop, right? Minus 2Vx because current is leaving from here. Minus 2Vx plus 2 I2, I3 minus I2 plus 2 I3 minus I2 equal to 0. Now substitute what is Vx? Vx is nothing but here I1 4 times rearrange this one, you get Vx is equal to I3 minus I2 if you rearrange this equation, same like the previous. Now third loop, 4 times I2 minus I1, 4 times I2 minus I1 here, 4 times I2 minus I1 plus 2 times I2 minus I3, 2 times I2 minus I3 plus 6I2 plus 6I2 equal to 0. Now solve this equation. 12I2 minus 4I1 minus 2I3 equal to 0. 12I2, you just rearrange this equation, you will get 12I2, I1 and I3, one equation. I1 equal to 5, another equation. Substitute I1 here. Then we need I3. How many equations we have? Yeah. We have, this is one equation and this is one equation. Now substitute, that is 4, what is Vx? Vx is nothing but 4 times I1 minus I2, right? So solving this equation, I2 will become 10 by 3. Now VThevenin is nothing but V0 VOC, that is VOC is equal to 6 times this. VThevenin is nothing but VOC, that is nothing but 6 times I2, 6 times I2. What is 6 I2? We got it 10 by 3. So 6 multiplied by 10 divided by 3, that is 20 volts. So this is how we find the Thevenin's equivalent circuit. 20 volts is the Thevenin's voltage and 6 ohms is the Thevenin's resistance, what we find in previous slide. So like this, when dependent sources are there, we have to find R Thevenin's by applying a voltage source across the AB terminal with 1 volt or more, up to you, or a current source across the AB terminal. Then we can find the, with loop analysis or mesh analysis, node analysis, we can find what is the current there. Then we can divide it V0 by I0. Then you will get the RThevenins. Same, apply the original circuit and find the VOC, open circuit voltage at terminal A and B. By using mesh analysis and node analysis, we can find VOC, that is voltage across 6 ohm resistance, is nothing but your Thevenin. So we got this solution. What is the time? Yeah, the Nortons we'll do in the next class, inshallah.